Chapter 2, Lecture 3. In this particular lecture, we're going to take a look at boundary and initial conditions. So once we determine what differential equation we have to solve, we use the boundary conditions and initial conditions to eliminate any unknown constants in the problem. So in this lecture, we're going to look at boundary and initial conditions. So once you have your differential equation for the heat transfer problem you're trying to solve, in order to solve it, you need what's known as boundary conditions and initial conditions. That will satisfy any unknown constants that you have in the problem. So let's look at the various types of boundary conditions. So the first type is that you specify the boundaries on some surfaces. So for example, here, if you have a planed wall that's a thickness L, so it's on one side of the wall, it's 150 degrees C. On the other side of the wall is 70 degrees C. So, since the temperature is a function of position and time, the temperature at 0, so this is the x-axis, the temperature when x is 0 at any time is equal to 150 degrees. On the other hand, the other boundary condition, this is the temperature at L, when x is L, at any time is 70 degrees C. So, in this case, once you solve your differential equation, you can use these boundary conditions to determine any unknown constants. So these temperatures here can be constant, which they are in this example, or they could be functions of time as well in the more complicated case. The second type of boundary condition we can run in is by specifying the heat flux on the boundary. So remember, heat flux is Q dot equals minus K times the partial of T with respect to X. And this is defined such that with the negative sign, it's in the positive X direction. So let's take a look at for a plate of thickness L subjected to heat flux of 50 watts per square meter into the medium from both sides, for example, like the shown here. So here the heat flux is coming in the positive X direction. So it's positive 50, and here it's again positive X direction, so it's positive 50. A special case is when you have what's known as an insulated boundary. In that case, the heat flux is 0. So here's a case where the left side is insulated. So therefore, the partial at T with respect at X equals 0, and any time it would be 0. And the left-hand side has a condition 1 boundary where we specify the temperature at L as 60 degrees for all times. So it shows you can have these mixed kind of conditions. You don't have to have both insulated on both sides. Another special case is where you have thermal symmetry. That's a case where you have something like this here, where the temperature distribution is symmetric with respect to the center of the plate. This is a condition where the heat flux at halfway is 0. So it's a 0 slope up here at the top. So you could have a case where it was bent this way or bent this way, but the slope is 0 at the top. So let's take a look at an example 2.6. We have an aluminum pan on top of an electric range. The bottom section of the pan has a L of 0.3 centimeters thick. So that's the thickness. It has a diameter of 20 centimeters all the way across. Electric heating unit on the top of the range consumes 800 watts. And 90% of the heat generated in the helium element is transferred up to the pan. During steady state operation, the temperature of the inner surface of the pan is measured to be 110 degrees C. Express the boundary conditions for the bottom section of the pan during the cooking process. So in this problem, we know this has a rectangular symmetry. We're going to look, even though the pan is circular, we're only looking at a small section here, so it's it's a rectangular symmetry. So we go back to our lecture 1 where we showed what the equation was, and so clearly this pan is only a function of x. It's not, I'm sorry, of z up and down. It's not a function of X or Y. And in the figure here, the book uses an X here as up, but I like using up as Z, so I've replaced it with a Z here. So this term and this term are 0, and you end up with this equation here. Now, we're told that what's the boundary condition? Well, the boundary condition on the outer surface of the bottom of the pan can be approximated as being specified heat flux. It's stated that 90% of the 800 watts. So what's 90% of 800 is 720. So we have this kind of condition here where we're specifying the heat flux on the bottom of the pan. So what's the other boundary condition? We're told that the temperature of the inner surface of the bottom of the pan is 100 degrees C. So the boundary condition on this surface is 110 degrees C. So if you have your pan here, you got heat flux coming up through it, and on the other side of the bottom and the other side, you have the temperature specified. So you have this mixed kind of boundary condition again. So the third example is what's known as the convection boundary condition. So for one-dimensional heat transfer in the X direction, in a plate of thickness L, the convection boundary conditions have to exist on both sides. So the heat conduction at the surface in a selected direction has to equal the heat conduction at the surface in the same direction. So here, for example, again, we show a wall of thickness L, and so on one side you have convection, right? So we have a convection equation here. That has to equal conduction on the other side. So you end up with this equation here where you have convection on one side and conduction on the other, and these are at an X equals 0 value. Well, so that's one boundary condition. The other one, you have exactly this similar kind of situation when X is equal to L. You have the conduction through the plate has to equal the convection when it gets out the other side. So you end up with these two kind of boundary conditions. Now, what's H1 and H2? Those are the convection heat transfer coefficients. The T infinity 1 and T infinity 2, those are the temperatures, out here on the surrounding media. So, for example, T infinity 1 is the temperature out here away from the wall, and T infinity 2 is the temperature out here on the right end of the wall. And then you have these constants, H1 and H2. Those are your convection coefficients. The third type is, so this is again the convection boundary conditions. These are equally applicable when the heat transfers in the opposite direction for one or both surfaces. Since the reversing of the direction simply reverses the sign. That's all it does is reverse the sign. So for example, if the convection, you have the case where you have convection and conduction, you have the negative sign. If you have the case where you have convection is going to the left, the negative sign gets lost and it's a positive. So here's an example, tube 7. You have steam flows through a pipe shown here, and it's obviously a cylindrical kind of symmetry. So here, steam flows at an average temperature of 200 degrees C. That's the steam inside of it. So here you have the inner and outer radii of the pipe are 0.8 centimeters and 8.5 centimeters respectively. So we're going to have a case where we have, a conduction kind of problem. So this is cylindrical symmetry, so we can write down the general equation for cylindrical symmetry for heat conduction. And here, it's not a function of Z or phi since it's symmetric. So you can get rid of those and you're left with this situation here. So the heat conduction equation simplifies this here. Now let's take a look at the boundary conditions. So you have the cylindrical heat flux in the radial directions given by this equation. And so you have this one to worry about, and you also have the fact that the heat transfer within steam in the pipe, that's a conduction condition. So you have this condition here to satisfy. So here at the inner surface, when R is R1, you get R1 here and R1 there, and T infinity is the temperature in here. K and H are respective constants. Then on the outside, it's said to be well insulated. So what does that mean? Well, that means that the heat loss through here is considered negligible, right? So these are pipes like you wrap, right? You put insulation and wrap them, so nothing's getting through that. So this is zero. So that's a pretty simple kind of case, when it says, you have to kind of pay attention to the problem when it says it's insulated. Well, that's what it means. So it gets rid of one of the boundary conditions. So the fourth type is what's called the radiation boundary condition. This is a case where the heat conduction at the surface in a selected direction is equal to the radiation exchange at the surface. Well, it's similar to the conduction convection, but the equations are different, right? So for the radiation, you get this equation here, right? So on both sides, you have a radiation conduction, conduction radiation. You get this equation for when x is 0, and you get this equation when x is L. And the epsilons and the gamma, and the rows here are determined by what this is made of. So the fifth type of boundary condition is what's known as the interface boundary conditions, where you have two different metals that are substances that are put together side by side. So they're in contact. So here they have to have the same temperature where they meet up. So that's pretty easy to establish this condition here, where x0 is so you put 0 here, you put the x-axis here. Well, someplace where they meet up, call that x0. That's what it has to equal. So you have this has to equal that. And finally, the last case is when you have the generalized boundary conditions, where you have conduction, convection, and radiation all simultaneously. So again, that turns into, you just have to match up stuff at the surface and pay attention to exactly the boundary conditions. We won't see a whole lot of these cases where we have all three of these, but the book does point it out.